Welcome to this tutorial on the thin filament as well as actin, the second in the tutorial series on myofilaments that you'll find within your sarcomere. And while I'm writing down here what we have up on the screen, I'll just point out straight away that lots of people get the term actin and thin filament confused. Now, although your thin filament does contain a large amount of actin, it's not the only structure, so don't accidentally refer to your thin filament as actin only. Okay, so I've got everything up here, the sarcomere, our thick filaments in red, our thin filaments in blue, and our actin subunits down here in blue as well. Now we can get started on the first and most important part of the thin filament, the actin itself. Actin is going to be a globular protein, globular meaning somewhat spherical and semi-water soluble. And because we have several different types and arrangements of actin, we refer to these subunits as G-actin. And our G-actins are going to be where we will find our myosin binding sites. So G-actin contain the myosin binding site, and I'll show them down here. So we've got these individual actin subunits down here, our G-actins. So we've got a few of them there, and we can see that they have a binding site on them. So they've got this binding site here, and also here. And this is where the myosin of our thick filament is going to interact with our actin. So it's the binding site. But if you look on the thin filament, you can maybe see straight away that these binding sites are covered by something at the moment. So myosin can't just automatically bind onto here. Something needs to happen first. And we'll get to what that something may be very soon, but before we do, let's have a look at what we call an actin chain. Now we can see that we do have these chains of actin here, and when they form a chain like that, we refer to it as F-actin. F for filamentous or fibrous. So we've got all of these here, and our thin filament is going to have two of these F-actin chains, and they're interwoven together. So they're interwoven strands in a helical kind of shape, similar to the tail of our individual myosin molecules. And I'll just put up here as well. So we've got the actin subunits we refer to as G-actin, but when those subunits polymerize into these long chains, we call it F-actin. So the G-actin is globular, and our F-actin is filamentous or fibrous. And those two fibrous chains are going to form the backbone of our thin filament. But we also have these other structures on the thin filament, and they are going to be regulatory proteins. And the regulatory proteins are going to have roles in contraction. Now I'll tell you what those roles are right now. The first of the regulatory proteins is something called tropomyosin. Now tropomyosin I've just highlighted here on the thin filaments in orange. So that's our tropomyosin here. And we can see them winding around the thin filament, covering all of the active sites on our actin. Now it's a rod-shaped protein, and as I just said, it's going to block the myosin binding sites. But blocking your myosin binding sites on the actin will be a good thing. It's a regulatory function. This is going to stop your muscles being inappropriately contracted when you don't want them to be. And I'll show that up here now on the thin filament as well, that this tropomyosin is blocking all of these binding sites. Myosin can't bind. And if your myosin can't bind, we're going to need something that's going to control when it can. And that's the second regulatory protein, troponin. Now troponin is made of 3 polypeptides, and each of those individual polypeptides is going to have a specific binding site for a different compound or molecule. So I'll show them up here on the thin filament. So we've got them all there in that teal kind of color. And as I said, it's made of 3 polypeptides. The 3 polypeptides are called TNI, TNT, and TNC. Starting with our TNI, it's going to be what binds actin. So TNI binds actin, and it's going to be inhibitory. So it's inhibitory in its role. So remember TNI, I for inhibitory, and I've just circled it on the bottom of all of these 3 polypeptide chains. Now our second polypeptide is going to bind onto the tropomyosin, so our rod-like protein tropomyosin, and it's going to help with the stability of these coils in the thin filament. So it's helping with the stability, and I'll put that as the second polypeptide on the troponin there. Which is going to leave us with our last polypeptide, TNC. And TNC is going to bind calcium and initiate the events of contraction. So I'll put the TNC right on the top here, and we'll see it from underneath as well on the second actin chain. And we've got this Ca2+ floating around inside the cell, and it's going to be able to bind onto that TNC. And when it does, it can initiate the rolling around of that tropomyosin, so the active site for myosin becomes available. So just to recap, our TNI is inhibitory, our TNT is for tropomyosin, and our TNC is for calcium. Lastly, with our troponin, we're going to find them roughly 1 in every 7 actins. So they're going to control a group of 7 actins availability to that myosin when we have calcium in the cell. And with that, we've covered all of the individual components of our thin filament. We know how they join together, how they interact, and what they do, but we don't know yet how it all actually happens when an action potential is sent into that cell and contraction is initiated. So now that we know everything about our thin filament and thick filament, we can talk about the contraction itself. I hope this video has been helpful to you guys. As always, thanks for watching, and I'll see you all again soon.